So this video is going to be on the trapezoid rule. So the trapezoid rule works just like those rectangles did. So instead of having rectangles next to each other to find the area underneath the curve, you're going to use trapezoids. So a trapezoid can look a couple different ways. This is a regular trapezoid. You guys have also seen isosceles trapezoids, which look kind of like that. And when we use trapezoids to find the area underneath the curve, we're going to be talking about this shape right here. And so in a trapezoid, this right here is the height. We have the top base and the bottom base. So the area of a trapezoid is 1/2 times the height times the top base plus the bottom base. And for height, I meant to write an H instead of a 1. That was my bad. Okay, so there's our formula for area of a trapezoid. So if we look at a curve, I just want you guys to be able to see maybe how this would look. So let's say here's our curve, and if we divide this up 1, 2, 3, 4, 5, we'll see how this works. So if I was to make this be one of my subintervals, there's my trapezoid right there. And you can see that this right here is actually the height of the trapezoid. And then here is, I'm going to say, my left base and my right base instead of my top and my bottom. And then we've got this trapezoid right here, so it's a little bit less slanted. And so again, there's the height. And we've got our left base and our right base, and you can see that the bases would be calculated by plugging these x coordinates into the function to see where that y coordinate is on the curve. So here, the height of the trapezoid is going to be the width of the subinterval. And the bases are going to be the function. I guess I don't need to write the word function. I can just say f evaluated at x. All right, so I'm not gonna, you guys can kind of see how this would work here. There's another trapezoid. It just kind of goes the other way now. So I'm not going to draw those all out, but you can see how that would be. And this is a little bit more accurate as far as making our guesses, because these are not all overestimates or all underestimates like we were accustomed to with the rectangles, but these they fit the curves a little bit better. So we're going to continue on with that same curve we looked at before, y equals x squared, and we're going to calculate the area underneath the curve on the interval from 0 to 1, and just we want to see how our guess is different now that we're using trapezoids instead of rectangles. All right, so there's the area we're trying to find. So I'm going to say the area using trapezoids, and I'm using 4 of them, and I'll go ahead and label my x's. I've got not 1/2, that's 1/4. So 1/4, 1/2, 3/4. So if I look at my first trapezoid, I'm going to say that the area of the first trapezoid is 1/2, the height of the trapezoid is 1/4, and then the left base on this one would actually be 0, and the right base on this one would be a height of whatever I get when I plug in 1/4. So my first height is what I get when my first base. My left base is what I get when I plug in 0. My right base is what I get when I plug in 1/4. So that's the first trapezoid. The second trapezoid right here, the height is 1/4 again. So 1/2 times 1/4. And then the left base is what I get when I plug 1/4 into the function. The right base is what I get when I plug, sorry, you couldn't see it, 1/2 into the function. So there's my second trapezoid. The third trapezoid also has a height of 1/4, So I got 1/2 times 1/4. The left base is what I get when I evaluate the function at 1/2. The right base is what I get when I evaluate the function at 3/4. And then I have my last trapezoid. And this is also going to have a height of 1/4. And the left base is what I get when I evaluate the function at 3/4. And the right base is what I get when I evaluate the function at 1. Okay, so that's a mess. Clearly we want to be able to shorthand this a little bit so we don't have to write all these things out. So this is how people typically shorthand. If you can see, this 1/2 shows up in all 4 of our trapezoids. So does the 1/4. And so since that shows up in all of them, we can take that out and put it kind of in the front, just like we did when we were looking at the rectangles. And then if you look at how you're evaluating this function, you're going to evaluate it at 0 to start with. So that was our left boundary. And then the 1/4 actually gets evaluated twice. So I'm going to say I'm evaluating the function. I don't know how I combined those two words together. Evaluate the function twice using 1/4. And then here you evaluate the function twice using 1/2. Oh, that's an F. And then you're going to evaluate the function twice using 3/4. And then this other endpoint only gets used once. So that's kind of the shorthand if we think about everything we're doing. So you're going to notice that when you use this left base and right base, 0 and 1 only get to be, 0 gets to be the left base of the first trapezoid, 1 gets to be the right base of the last trapezoid, but all these other numbers get to be the left base of one trapezoid and the right base of another. And that's why they're all used twice. So now we can go ahead and type in our y equals, we can put the function x squared, and then we can use our calculator and that function option to type these all in rather quickly. So I'm going to hit vars and then y vars. I'm going to say the function evaluated at 0 plus 2 times the function evaluated at 1/4 plus 2 times the function evaluated at 1/2 plus 2 times the function evaluated at 3/4 plus the function evaluated at 1. Oh gosh. Ta-da! And if you guys remember, the actual area was 0.3333333, so this gets us pretty close. So we're going to say, if I use the trapezoids, I get 0.34375, which is 11/32. Instead of 11/33, so that's pretty close. All right, so when we figure this out, you're going to calculate how wide your subintervals are the same way, or in this case, the height of your trapezoid. So we're still going to say we're going to do b minus a divided by n. So the upper end of your interval minus the lower end of your interval divided by however many intervals you should have. And we're going to say that when we do the summation of all this stuff, so using our intervals, we're going to have 1/2 times delta x. So that delta x, however wide each interval is, becomes the height of your trapezoid. And then we're going to plug the initial value, or the lower end, that a value, evaluate the function at that lower end. And then it's going to be 2 times the function evaluated for the next number up, and then the next number up, and then that pattern is going to continue until we get to the end, and at the end we're going to say 2 times 1 less than our interval, our subintervals, and then the last one is just going to be f of x sub n. So we know that this pattern holds true where the very left side and the very right side just get to be used once, and then everything in between gets used twice. Right, so this is very typical for these problems. So here, what you'll notice, because when we were doing rectangles and we were using the left endpoint and the right endpoint, we wouldn't necessarily use all of our xi values. We would find all those xi values, and maybe if we were using the right endpoints, we would skip the first one. Or if we were using the left endpoints, we'd skip the last one. Or if we were using the midpoints, we wouldn't use any of them at all. And the difference here is when you use trapezoids, you use every single one of those values. Right. So one thing to note, and this is very important, is that this procedure for rectangles and trapezoids, so the procedure we've used, and by the procedure we've used, I mean this like shorthanding it and putting it all in parentheses and adding a bunch of things repeatedly and using the limit notation and all of that stuff that we've done. It only works if the subintervals are of equal width, all right? So the procedure we've used only works if the subintervals have equal width. Right, so if not, find the sum individually. And when I say the sum, I mean the sum of the areas. I guess I could say that, sum of the areas. All right. So if they're equal width, then you can kind of shorthand what you're writing and multiply everything out that way. But if not, then you have to find the area of one thing and the area of the next thing and the area of the next thing and kind of add them all together. Okay, so we're going to go ahead and do 3 examples. So the first one says snow is falling. And we're going, it's over a 3-hour period. I guess I could include that. We're going to say over a 3-hour period. And we're going to approximate the amount of snow that fell using trapezoids. So we've got a table, and we have T, which is in terms of hours, that's our time in hours, and then R of T is how many inches per hour we have of snow. So when they started measuring the snow at 0, they had 0.7 inches. And then after the first half hour, they had 1.2 inches. And then after the first hour, 2.3. And R of T is inches per hour, so I'm saying 1.2 inches per hour for that one. So this is kind of a rate of change here. At 1.5 hours, it's 1.7 inches per hour. At 2 hours, it's 1.1 inches per hour. 2.5 hours, it's 0.5 inches per hour. And then at 3 hours, it's 0.2 inches per hour. So if these are all the different rates of change that we have, then when we add up all those together, how much snow would have fallen? So here, we're going to say, all right, they're asking us to use 6 trapezoids. If I look, I can see that these, remember the distance between these actually ended up being the height of the trapezoid. And if you look at all of these, you can see that all of these are 0.5 away from each other. So that means the height of every single trapezoid is the same. So I'm going to maybe write this as a note to myself for future reference. These are equal subintervals, which is good. I like that. So my area, I'm going to do 1/2 multiplied by the height of the trapezoid, which is 0.5. And then if I use kind of what I know about evaluating these, I'm going to say that the function evaluated at the first number gets used once. And then the function evaluated at each of these numbers gets used twice. So plus 2 times 1.2 plus 2 times 2.3 plus 2 times 1.7 plus 2 times 1.1 plus 2 times 0.5. And then the last one only gets to be the right base, so I'm going to say just 0.2 at the end. And then that's how I could use the trapezoids to calculate the area underneath the curve, which in this case means how many total inches fell if we're adding up all the inches from those rates of change. So if we go ahead and type this into our calculator, we're going to find that the total number of inches that fell in that 3-hour period would be 3.625 inches, and that's not an exact measurement, that's approximating it. All right, here's our next example. We're going to use the trapezoid rule. To approximate the area under the curve y equals x squared plus 1 on the interval from 1 to 4 using 3 subintervals of equal width. So here I'm going to go ahead and figure out what my delta x is. It would be 4 minus 1 divided by 3. So b minus a divided by the number of subintervals I have, which is 3 over 3. So that means the width of each trapezoid is 1. So I'm going to say I'm using 3 trapezoids. I have 1/2 multiplied by the height of the trapezoid, and then I'm going to evaluate the function on the left end of that, so that would be plugging in 1, and then I'm going to have 2 times the function evaluated. I move over 1, so evaluated at 2, 2 times the function evaluated at 3, and now I'm at the other endpoint, so I don't do 2 anymore, I just say the function evaluated at 4. And then we can go ahead and practice plugging this in, and if you have a graphing calculator at home, I do want you to practice to make sure that you're good at plugging these in. So times, and I guess I should plug this in, x squared plus 1. So now I've got vars evaluated at 1 plus 2 of this is evaluated at 2 plus 2, the function being evaluated at 3 plus the function being evaluated at 4. So 24.5 should be what you get. So the area underneath the curve would be 24.5 units squared, and I'm literally going to write units squared because it's a graph and I don't know with the graph paper what those units are. Okay, then here's our last example. We have a function that is continuous on 210. So if you guys remember when we were finding the area under the curve, the function had to be continuous. And we're going to use trapezoids to approximate the area. And they don't give us an equation, they actually just give us a table of values. So when x is 2, y is 5. When x is 6, y is 15. When x is 7, y is 17. When x is 10, y is 11. So if you look here, your intervals go from 2 to 6, 6 to 7, 7 to 10, and you should notice that those are not equal. So unequal subintervals. And so that means that we have to do these trapezoids separately. So our first trapezoid, 1, 2, 3, there's 4 of these. Our first trapezoid is 1/2. The width of this is 4, so that's the height of the trapezoid, and then base left base and right base. And then we've got 1/2 the height of the next trapezoid is 1. And then we've got the left base and the right base. And then our third trapezoid, that was not 3, 4, that was 3 trapezoids. My bad. And then we got 1/2, the height of this trapezoid would be 3, the left base and the right base. And you could shorthand this, I guess, if you wanted to take out the 1/2. I don't know how much that's really going to shorten this procedure for you. So this would be 98. And here we don't know what the units are, so I'm just going to say units squared.